The two long diagonals on a times table grid have been shaded. What is the sum of all the shaded squares? When you've got an answer, consider how did you do it and what strategy did you use, and can you maybe find a more efficient way? And where else could you go with this task? So the most natural thing to do, I guess, is maybe try and start adding up the diagonals individually, and pupils will probably quickly find that there's no easy or systematic way to do this. So the trick is to start considering the two diagonals together. So if you look at the 1 in the 10, in the top left and the top right, if we do 1 plus 10, we get 11. Nothing to spot yet, so let's try the next one, which will be 4 plus 18. And straight away, hopefully, pupils will notice something at this stage. So we've got 11 and 22. So we're talking about the 11 times table. And the 11 times table is quite important for this whole task. The third row, well, we're going to predict now, or make a conjecture that it's going to be 33. So we get 9 plus 24, which is right, 33. And we can test it all the way down, but basically we're going to end up with the 11 times table all the way till we get to the bottom row, which will be 10 plus 100, which is 110. So we've simplified the task massively now, because we know each pair of numbers is a number in the 11 times table. The question is then, how many 11s are we going to have here? Because we've got 1 11 there, 2 11s there, 3 11s there, and so on. So I always joke that triangle numbers seem to appear from nowhere, and here they are appearing again. Essentially, we need to add up all the numbers from 1 to 10, and then multiply that by 11, because we've got 1 11 there, 2 11s there, 3 11s there, and so on. So how are we going to add up all the numbers from 1 to 10? Well, you might have seen some of my Q&A videos on these triangular numbers, but essentially it's just a case of 1, 2, 3, 4, 5, and then 6, 7, 8, 9, 10, and we get 5 pairs of 11. 1 plus 10 is 11, 11, 11, 11, 11. And you can demonstrate this nicely using Cuisenaire rods. So, the numbers from 1 to 10 is 5 lots of 11, which is 55. So we've got 55 lots of 11. I told you 11 was important in this task. So that's going to be, well, 550 plus another 55. The total of all the shaded squares is going to be 605. Okay, so where else could we go with this task and behave mathematically with it? Well, I suggest that this would be a really nice task to do when you've done quadratic sequences, because the first diagonal, the one that runs from 1 to 100, is obviously just your square numbers, so that has an nth term of just n squared, obviously. The second diagonal is a little bit more interesting, the one that goes from 10 to 10, so I've written down the terms of the diagonal here. Now this also forms a quadratic sequence. You can see the first difference here is changing by 2 each time, so we've got plus 8, then plus 6, plus 4, plus 2, plus 0, and so on. And the second difference is the constant one, so negative 2. So you can see, if you taught quadratic sequences, pupils should be familiar that this here gives a quadratic sequence where the first term is going to be negative n squared. Remember that halving that coefficient of a and so on. So we're assuming knowledge of pupils have got this knowledge of forming quadratics. So how can they apply it to here? Well, we're going to have negative 1, negative 4, negative 9, negative 16, and so on. So there's my negative n squared. And how do I get to the terms in this sequence, this diagonal from 10 to negative 10? Well, here it's going to be plus 11. And then here, we've got plus 22. And here, alarm bells should be ringing. Hang on, here's this 11 times table coming again. Is this one plus 33? Yes, it is. And then plus 44 and so on. So the nth term of this second diagonal is negative n squared and then plus 11n. So now what happens if we add these two nth term rules together? So if I add the first diagonal to the second diagonal, well, the first diagonal has an nth term of just n squared. If I add the second one, well, I'll be adding in a negative n squared and a plus 11n. Now obviously those just cancel out to give me an nth term rule for both sequences combined of just 11n. which is what we got to when we did it just numerically. So how am I going to add up all these terms again? Well, I need to work out when n is 1, n is 2, n is 3, all the way up to 10. And we end up doing exactly the same maths. We end up with 55 lots of 11 to give us that answer again of 605. So it's a nice link that you can make, so that the task can be used with any pupil. But then once you've done quadratic sequences, then you might want to show this nice link that you can make as well.